Good evening, everyone. So today I'm going to show you, guys and girls, how to use OpenRocket, which is an open source rocket design tool. And you're basically going to be using this tool to design and to simulate your G64 rockets. So let's go ahead and get started. I'm going to go and share my screen. All right, so this is OpenRocket. This is the main interface that you'll be working with in the rocket design tab. We have the Mortar Configuration tab, and we have the flight simulation tab. So we're gonna start off in the rocket design tab. So in the top left, you can see a little modeling tree. And it doesn't really look like a tree right now because we don't really have anything in it. But this is basically a hierarchy of all of your rocket components. On the top left, on the top right, you have the components list. So here are all of your basic components, such as your nose cone, your airframe, body tube, a transition if your rocket is going to be, if your rocket is going to have a body tube that changes its diameter throughout the length, a bunch of fins, trapezoidal, elliptical, freeform, launch lugs, and you also have inner components, which are structural components that is going to be inside of your airframe. For example, an inner tube, which is going to hold your motor casing, a coupler, which is used to join different rocket sections together, centering rings to hold your inner tube or your motor tube in place, bulkheads to seal off different rocket sections, and engine blocks. And if you look down, you have mass objects. So these are other components that are either used for recovery or for experimental purposes. So every rocket needs a parachute. So you have one here, a streamer, a shock cord, which is used to connect the parachute to the airframe, and a mass component. If you're throwing anything else in there, either it can be a scientific payload or any other retention system that isn't listed in this list. So for a G64 rocket, you're going to be working with mostly a craft phenolic body tube, pretty much a very hardcore variation of cardboard. So the first thing first, you're gonna need a nose cone. So let's go ahead and put that in. So just double click on the nose cone. Oops, we got an extra one. There we go. And if you wanna adjust the geometry or the material properties of this nose cone, you're gonna go into the tree up here and you're gonna double click on nose cone. It's not showing up. All right, there we go. So here's your nose cone configuration. You can edit its name and you can give it its shape parameter. So a conical would be a triangle with straight sides if you were to look at it from the side. And you have other geometries such as an ogive, ellipsoid, power series, parabolic series, and a hack series. And all of the descriptions are beside in this little box where you can read more about it. So part of the components for the G64 kit includes an ogive nose cone, and the length of the nose cone. So once you receive your components, you're basically going to have to measure it using either a ruler or a caliper. So we're going to set our nose cone length from 9.5. And this nose cone is basically a 4:1 nose cone. What that means is that the length of the nose cone is 4 times the diameter of the base. So this is your body tube that you're going to receive. So what you want to do is you're going to measure its diameter. So the exterior diameter of this is about, not sure if you can read it, 2.28 inches. So you're going to put that in as a base diameter. There we go. And you're going to change the cardboard material, you're going to change the material to polycarbonate because that's the material of the nose cone. All right. So that's your nose cone. So the next component that you're going to have is the body tube. So again, just double click on the body tube component. And I believe the length of this body tube is 36 inches. So you're going to type that in, 36 inches, and your outer diameter, if you set it, if you click the automatic button, it's going to match whatever you have on the nose cone, which is very convenient. So you don't have to keep typing in the same diameter for every component that's going to be in line with each other. So your inner diameter, again, you can use the calipers and measure it. So that's about 2.13. Right there. And your component material is going to be craft phenolic. Go ahead and close it. So now you're going to have other components within the body tube. So the most important part is your mortar tube to hold the rocket motor casing. So you're going to double click on the motor tube. Okay, maybe I should stop double clicking it. Now, as you can see, if you look up in the tree, the mortar tube is listed beneath the body tube. What that means is that this component is actually going to be inside the airframe. If you list it underneath nose cone, then it's going to be inside the nose cone, but you don't want that. So let's go ahead and put it back. And this mortar tube is a much smaller material in diameter, like that, compared to the airframe, as you can see. So after measuring those component inner and outer diameters, you're going to list them in. So 1.22 inches. And the inner diameter is 1.062. And it's going to be 6 inches long. And again, don't forget to update your component material to craft phenolic. And of course, you can change its position relative to whatever component that it's listed under. So right now, it's in the body tube. So if you drag this slider, you can change where this component is relative to other components. So you want it to be right at the back of the airframe. So I'm going to put that 0. There we go. And go ahead and close. So now, obviously, you can't have this motor tube inside the airframe like that. There's nothing holding it in place because the outer diameter is not the same as the inner diameter of the body tube. So you're going to need a bunch of centering rings in order to hold this motor tube in place. So you're going to click on centering ring. Now, if you highlight inner tube and you click on centering ring, the centering ring is going to be inside the motor tube, which is not what you want. This centering ring is going to sit in between your inner tube, aka the motor tube, and the body tube. So you're going to delete that, highlight body tube, and click on the centering ring. There we go. And now the great thing about this tool is that if you click automatic, it's going to automatically size the outer diameter of this centering ring to be the inner diameter of your body tube. And again, the inner diameter of the centering ring to be the outer diameter of the inner tube. Basically, everything fits. So just click automatic and change its thickness to 0.125. So you guys are basically going to be laser cutting these centering rings using the laser cutter in either the Projects and Prototyping Lab or Project Innovation Hub. And it's going to be made out of I believe it's plywood. Yeah. So change that material. And we're going to call this the 4 centering ring, because every rocket needs a minimum of 2 centering rings. You can't have just one. You got to secure it at least both ends. So we're going to name this one the 4 centering ring. And we're going to position it somewhere near the top, right there. Let's call it 5.75. Go ahead and close it. Again, select the body tube and click on centering ring again. And name this one the aft centering ring. Again, both of these are automatic in terms of the outer and inner diameter, so you don't have to worry about that. Change its thickness to 0.125, which is 1/8 plywood. And change its material property to, change its material to, where is plywood? There we go. And place it somewhere near the bottom. Just like that. All right, so we're gonna go ahead and close it. Now the next component that you're gonna need once you have your booster section or the motor assembly section set is your fins. So the whole purpose of the fins is to reduce, or should I say, move the center of pressure of your rocket further back. So if you look at this, if you look at the diagram on the bottom of the screen, you can see that your center of pressure as of now, which is the red dot, it's 4.413 inches from the tip of the nose cone, whereas your center of gravity, which is where the rocket is balanced, is at 25 inches. And obviously your stability caliper is negative 9.05. And you don't want a negative stability caliper. You want the center of pressure to be behind the center of gravity. So in order to do that, you're going to use fins. So there are a bunch of different fin sets here, but you're going to choose the trapezoidal fins. So if I move this out of the way, you can see that the fins are being reflected in the diagram at the bottom. You can go ahead and change the number of fins to 2, 3, 4, 5, or whatever you want. Conventional is either 3 or 4. In this example over here, we have 4 fin slots that are cut out, so I'm going to use that. Now, if you change the root cord, you can see it being updated in the diagram. So the root cord is basically the length of your fins that is parallel to the body, the rocket body. And the part where it's the closest as well. So you can change this to whatever value you want. Let's say 6, let's say 5, right there. There you go. And your tip cord is the length of the tip of the fins. So if I increase the tip cord, you can see how the ends get a lot longer. So I'm going to put that at 1. And the goal of this is to basically just to ensure that your stability margin is at least above 1. Right now it's 0.418. So okay, what can we do? You want to increase the surface area of those fins so you can draw the center of pressure further back. So let's try and increase the surface area by increasing the height of the fins. And we can see its effects. If we increase the height, your stability increases and your center of pressure moves further back. Just like that. And of course, you can also set your sweep length right here. Again, if your sweep length is longer, it's also going to draw the center of pressure further back. Let's go ahead and set it at, let's say 3. Let's position the fin so that it's right in between the 2 centering rings. All right, that's perfect. Now, you know what, just as an example, let me go ahead and make them a little bit longer. So I usually like to have my fins set up such that the very ends of the fins they aren't protruding out through the back of the rocket, or they aren't further back compared to where your aft centering ring is. And the reason is that if you go ahead and have a sweep length of, say, almost 8 inches, your rocket is going to impact the fins first, and your fins are fairly thin and they might break. And obviously you don't want that to happen. So I like to have them a little bit further up, just like that. All right, so that looks about right. As you can see, our stability is above 1. It's 3.11, so that is relatively high, which means our rocket is inherently stable. So let's go ahead and change the component material to plywood. Again, you guys are going to be laser cutting these components using the laser cutter. All right. And of course, you can change the cross sections such that it's rounded or airfoil shaped. So let's just keep it simple and go and keep it at square. And now the next thing is, if you look into this next tab here, so the fin tab is basically the an extension of the fin that goes into the body tube. So instead of your fins being mounted on the surface, it's actually going to protrude into the body tube, and it's going to be attached to your motor tube. This provides a much more secure attachment point. So basically, the fin tab is going to be epoxied on to the motor tube, and on the other hand, you also have, in addition to that, you also have fillets that are going to be applied on the exterior of the rocket. So you have 2 attachment points as compared to just 1. So structurally, this is a lot better. So your tab length is set to 1.969. You can go ahead and increase the tab height. As you can see, if you look at the diagram down below, that's basically your fin tab. So obviously now it's going through the motor tube, and you don't want that. So right at 0.5, you can see that it is in contact with the motor tube. And then you want to increase the length to get the maximum area that you can apply the epoxy to. So you can go ahead and increase the length or decrease it however you want, and change its position relative to the fin itself. All right. So you're going to go ahead and close it, and you can rotate this diagram to have a look at what your rocket's going to be like. All right, so your next component is going to be the parachute. So again, click on body tube, hit into the parachute section. And you're going to be having a 24-inch diameter parachute with a drag coefficient of 0.8. It's going to be made out of ripstop nylon. Basically, just leave it as it is. Oh, right, speaking about, don't just leave it as it is. You're going to position your parachute near the separation point. So your parachute is going to sit inside your body tube, right beneath the nose cone, so right about there. And of course, once you actually receive your components, you're going to try and pack it up and see what its dimensions are going to be. So I'm going to put the length as 3 and 2.2 inches. There we go. And since this is not a dual deployment rocket, you're not going to have 2 parachutes. So this is going to be your main parachute. And the only place to deploy it is at apogee, which is the maximum height of your rocket. All right. Next, you're going to have your shock cord, which is basically a string that is going to attach your parachute to the aft airframe and to the nose cone. So click on that. And typically you want your shock cord to be about 4 times the length of your body tube. So right now the length of our body tube is 45.5 inches multiplied by 4. It's going to be about 180 inches, 182. And it's going to be made out of tubular nylon. Again, you can set your pack length and your pack diameter. You can place it underneath the parachute. You're also going to need some launch buttons, which is used to hold the airframe to the launch rail and keep it guided until the rocket's going fast enough. So select on the body tube, and for your launch button, you're just going to use a mask component. Wait, let me have a look at this. Yeah, so you can just simulate that using a launch lug. I find that works better. So we're going to go ahead and set the length at 0.378. And of course, you're going to have to measure all of these components once you receive them. 0.39, 0.311. Yep, you can just leave that as it is. Now, the main point of getting these dimensions correct is because the launch buttons are going to be mounted on the outside of the rocket. So that will change its drag coefficient. It's going to change where the center of pressure is. So you want to get this right. All right, let's go ahead and put one right about there. And you're going to create another one. And you're going to place it at the very end of the rocket. And right there, you want this launcher button to leave the rocket last. Okay. So next, you're gonna need to have some form of motor retention. So you know what, let's go ahead and put a motor up in there and see what it looks like. So if you go into the Motors and Configuration tab, you can see that there are basically two components in which you can mount the motor. So you have a body tube and an inner tube. So your inner tube is your motor tube. So you're gonna click that. And why the body tube is listed here? Well, there are some rockets called minimum diameter rockets in which the diameter of the motor casing itself is almost the same as your airframe. So in that case, you wouldn't really have an inner motor tube because there wouldn't be any space. But in this case, we do. So we're gonna select the inner tube and we're gonna hit a new configuration. And we're gonna select the motor. And the motor is gonna be a G64 motor. I'm gonna click that and hit OK. So that's what it looks like when the motor is loaded into the rocket. And once you have a motor loaded in here, if you look at the bottom left, you can see that it has already generated a bunch of different flight parameters or rocket performance parameters, such as how high it's going to go. So right now, with the motor mass of 1.46 pounds and a stability margin of 1.85, length of 45.5, and a diameter of 2.28 inches, your rocket is going to travel to a maximum height of about 2,000 feet. And again, you can read the acceleration and the velocity. So with a motor like that, it's basically just free to slide in and out of the motor tube. You need some form of retention system to hold it in place, or else it's gonna just fall out the back of the rocket. So we're gonna go ahead and put a mass component. And this motor retention, it could be as simple as a little metal plate and a screw that's just gonna cover the very end or the lip or the circumference of the motor casing itself that prevents it from sliding out the back. So you're gonna name it the motor retention system. Unspecified. You're gonna give it a mass 0.125. So once you receive your components, you actually have to weigh them, and just so that OpenRocket's predictions are a little bit more accurate. And of course, it's a motor retention device, so it's going to be located at the back, right behind the motor. Next, what you want to do is you have another component that is used to attach the shock cord to the airframe itself. So we're going to hit that mass component, and you're going to be using a forged eye bolt. Let me go ahead and see if I can find one. All right, so this is what the motor tube and the centering ring is going to look like. As you can see, that's the motor tube, and you have your centering rings. So this is going to be inserted into the rocket. And this eye bolt is what you're going to be using in order to hold this entire booster assembly to the parachute or the shock cord. well, the shock cord is going to be attached to the eye bolt, and the shock cord is going to be connected to the parachute. So once you receive your eye bolt, you're going to weigh it on a scale, type in its mass, its length, and its diameter. So if you have your mass and your length and your diameter, you can approximate its density because you have your volume. And again, you're going to place this component right in front of your forward centering ring. Right there. Oh, there is actually one last thing that I'm forgetting, and that is your nose cone. So your nose cone right now, it's just sitting on top of the body tube. It's not actually inserted. So if you go ahead into the nose cone and you click on shoulder, this is it's basically like a little coupler attached onto the nose cone that will be inserted into your body tube. So the diameter of this nose cone shoulder is going to be the inner diameter of your body tube. So your inner diameter is 2.13 inches. So you're going to go ahead into your nose cone and type 2.13. And as you can see now, it's nice and snug with the body tube. And usually the nose cone shoulder should have a minimum length of half of the body diameter. So your body diameter right now is about 2 inches. Half of that is about 1 inch. So you can go ahead and list that as 1. And that's it. So you have modeled your G64 rocket in OpenRocket. Don't forget to go ahead and save it. Now, if you go to flight simulation, you can go ahead and create a new simulation to have, a predicted chart of, say, your time and altitude, and you can extrapolate a lot of information from that graph. So let's go ahead and try and simulate what this is. All right, so this preset plot will keep track of the vertical motion versus time. So on your x-axis, you're gonna have time with seconds as the unit. And for the y-axis, our main thing that we want to look at is the altitude. And there are a lot of different flight events in here in which you can select, and it will show you when those events take place. So motor ignition, motor burnout, apogee, recovery device deployment, and ground hit. Those are all extremely important. I would go ahead and add launch rod clearance in there, and that is basically when the rocket leaves the launch wheel. So once you go ahead, once you've selected what kind of events you want to analyze, go ahead and click plot. There you go. So listed in red is your altitude, and you can see how it changes with respect to the time. So if you look at this graph, your rocket starts to climb immediately when the motor ignites. So that's when the clock starts running, and it reaches its apogee at 10 seconds. And you want this time to coincide, or you want your parachute deployment or your ejection charge to coincide with apogee, with when apogee happens. So right now it's at 10 seconds. For example, if you have a look at the motor you have up here, see that? It says G64-4. So that -4 means that by default, your motor is going to your motor is going to have a delay of 4 seconds after it burns before it fires the ejection charge. And you want that time to coincide with apogee. So right now, if you zoom into the graph, or if you just look really carefully, you can see motor burnout right here. And if you look at when that time is, it's at about 2 seconds. So this motor is going to burn for about 2 seconds. So if you go ahead and add 4 seconds to that, so that means that your ejection charge is going to fire at about 6 seconds, which is right here. And that means that the rocket is still climbing at very high speeds, and then you're going to throw your parachute out. So that's not what you want. The reason why your recovery device here is automatically listed in, or it's automatically being deployed at the apogee, is because in your parachute file, on your parachute component, you have it set to deploy at apogee. So if you're using a delay grain, which is that little number behind your motor, just ensure that it coincides with the time when your rocket reaches apogee. If you're using electronic deployment, then you don't really have to worry about this, because your altimeter is going to sense when apogee happens. So it detects a change in your altitude based on the pressure, and the rocket says, okay, I detect that the rocket has reached its maximum point, it's going down, so I'm going to go ahead and fire the ejection charge and blow the parachute out. So if you're using an electronically deployed rocket, then you don't really have to worry about the time delay at the end right here. So once you go ahead and, once you've simulated your rocket launch, you can go ahead and have a look at its velocity, its off-road velocity, and usually you want this at a minimum of 50 feet per second. That's just a rule of thumb. There are a lot of other analysis methods in which you can go ahead and dive deeper into, but the rule of thumb is generally you want your off-road velocity to be about 50 feet per second. So we're almost double that. So this rocket is going to have a wild acceleration. You're going to reach an apogee of 1,852 feet. And again, with the parachutes and everything, you're going to have a flight time of about 90 seconds. So I hope that covers it. Once you receive all of your components, it's very important to weigh each and every single one of them. Go into the override tab and hit override mass and type its actual mass in, because all of these component masses in here, they are all estimates, and they aren't necessarily the same as what you're going to be receiving. So go ahead and do that. Follow the dimensions, build your rocket, and have a successful flight. So that would be all. Thank you very much.